I'd like you to start with this warm-up. Use synthetic division to divide the function there, f, by x minus 2. Then I want you to evaluate f of 2. The remainder that you get when you do the division is f of 2. Press pause on your video. When you're ready for the answer, press play again. My synthetic division is here. You'll notice I put the 2 up in the left-hand corner. That is what would make x minus 2 0. As I go down, I add. So across my top row, are the coefficients of my function, 4, negative 3, 2, negative 7, 9, and negative 5. I add 4 to 0 and get 4. Then I multiply the 4 and the 2. That's 8. And then I add down my column again. 5 times 2 is 10. That's what goes here. I add to get 12. I multiply again. That's 24. I add. That's 17. I multiply 17 times 2. That's 34. Add, get 43. Multiply 86. Add 81. So when I divide using synthetic division, the numbers on the bottom row are the coefficients of my quotient. And the degree of the quotient is 1 less than the degree of the function I started with. So 4x to the 4th, the 5 goes here, 12 there, 17 there. It goes in decreasing order of exponents. The remainder goes over what you were dividing by, x minus 2. f of 2 is 81. It's the same as the remainder. Next, I'd like you to factor this function. Press pause on the video. When you're ready for the answer, press play again. So, you were not able to factor it. Normally, when you see 4 terms, you think about factoring by grouping. This does not factor by grouping. However, there are zeros that go along with this function. It is factorable, so we need one more method to factor when nothing that we know of at this point works. So today we're going to talk about finding real zeros of higher order polynomials when they don't factor using traditional methods. So, looking at this function, what if I told you that 3 was a root? Remember, a root is the same as a 0. How might that help? Press pause. When you're ready to see the answer, press play again. Well, the way that would help is if 3 is a root, I know that x minus 3 is a factor. So if I take my function and I divide by x minus 3, or I use synthetic division with 3 being my root, I can find out that my remainder is 0. I know it should be because I was told 3 was a root. Then this factors as x minus 3 times the quotient that I get when I do my division. At this point, x squared plus 6x plus 8 factors further. I can factor that. So now my zeros are 3, negative 4, and negative 2. Now the trouble with this is you have to find a zero that works. And there are infinitely many possibilities. So there is something called the rational zero theorem. And what that says is that any potential rational root has to be in the form of one of the factors of the constant divided by the factors of the leading coefficient. So the way that this works is this. If I want to list my possible rational roots, I'm going to write out my factors of the constant over my factors of the leading coefficient. So, for whatever reason, we call these p's over q's. P's are the factors of my constant, so of negative 6, I have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. My leading coefficient is 1, so my factors of my leading coefficient are plus or minus 1. I then list the possible roots from least to greatest. So the lowest is negative 6, -3, -2, -1, and then 1, 2, 3, and 6. If this had been plus or minus 2, I would have had to take each one from my numerator and divide by the 2, take the 3, divide by the 2, and so on. But it's a 1. So these are all the potential roots of my function, all the potential rational roots. Now, there's another rule that helps us called Descartes' rule of signs. It says the number of positive real roots, real zeros, is either equal to the number of sign changes of my function or less than that number by an even integer. It also says the number of negative real zeros is either equal to the number of sign changes of p of negative x or less than that number by an even integer. And Descartes counts zeros with multiplicities higher than 1 as separate zeros. So if I had a 0 that's 1 with a multiplicity of 2, Descartes would count that as 2 zeros. Now, I'd like to use Descartes' law of signs to determine the possible number of real roots. Now, notice that says real roots. It does not say rational roots. Real roots include rational roots. It also includes irrational roots. So there are more options for Descartes than there are for rational zeros. So I have this function here, and I'm going to count the number of sign changes. It goes from positive to negative, so this counts as 1. It goes from negative to positive, it counts as 2. Positive to negative, 3. Negative to positive, 4. So there are 4 sign changes, or there are 4, 2, or 0 real positive zeros. It is the number of sign changes or less than that by an even integer. Now, as far as negative zeros, you have to look at f of negative x. So I plug negative x into my function. Anything with an even power, the negative doesn't do anything to, but anything with an odd power, it reverses the sign of the coefficient in front. So this becomes x to the 4th plus 9x cubed plus 25x squared plus 27x plus 10. And from this, you can see that there are absolutely 0 sign changes. So the number of negative real zeros is 0. One more thing that's going to help us in guessing and finding a 0 that works is this. It's an upper and lower bounds rule. If f of x is a polynomial with real coefficients and a positive leading coefficient, suppose f of x is divided by x minus c using synthetic division. If c is greater than 0 and the numbers in the bottom row are either all positive or 0, then c is an upper bound for real zeros of f. If my potential 0 is negative and the numbers in the bottom row are alternately positive and negative, c is a lower bound for real zeros of f. 0 on the bottom row of my synthetic division is a wild card. It can count as a negative or a positive, and that's true in both of these cases. I know it's hard to understand before you see an example. Take a minute, write this down. We'll go through some examples and it should all come together. So press pause, and when you're ready to go forward, press play again. So we're going to use everything we learned to factor this function. Looking at it, there is not one way I can group it to get it to factor, but it is factorable. The first thing I'd like you to do is I would like you to find the number of positive and negative real roots using Descartes' law of signs. Press pause. When you're ready for the answer, press play again. So you can see from my function, I have one sign change from positive to negative. So there is exactly one positive real root. I also found f of negative x. In this one, I have 1, 2, 3 sign changes. So I have 3 or 1 negative real roots. Remember, it's the number of sign changes or less than that by an even integer. Now I want you to use the rational zeros theorem to find the possible rational zeros of this function. Press pause on the video. When you're ready to see the answer, press play again. So I listed my p's over q's. I have all the factors of 24 in my numerator and all the factors of my leading coefficient in the denominator. And then I listed my possible rational roots from low to high. Now, unfortunately, it's time to guess, or I should say fortunately. Now, when I look at this, I have 1, 2, 3, 4, 5, 6, 7, 8 times 2 possibilities for rational roots, so 16 of these. Now, it may seem like a lot of choices, and it is, but you will have to admit it's less than infinitely many possibilities. Now, at this point, I have to decide, am I trying to find my real positive root or my real negative roots? I decided to go with the real positive roots first. So you just have to pick something and guess. When I do that, I'm pretty strategic in that I would like to find an upper bound if I can, because then I can eliminate some choices. So the first thing I guessed with was 6. And when I did that, I used my synthetic division. I listed my coefficients and found that the bottom row with my synthetic division was all positive. Because of that, I know it's an upper bound. And that's awfully nice because right now I know 6 doesn't work. I also know 8 doesn't work, 12 doesn't work, and 23 doesn't work because it is an upper bound and I don't have to check any of those. So now I'm narrowing things down. I have 4 choices here. So again, I have to just guess. Unfortunately for me, when I did this on my own, I had to guess 4 times. Sometimes you're much luckier than that. I usually am. I guessed next 3. I wrote my coefficients across my top row. I used my synthetic division, and I found my bottom row was all positive. So again, I said, oh, that's an upper bound. So I got a remainder, so it's not 3. So I crossed off 3, and I crossed off 4. And I said, all right, I have to guess. There's only 2 more choices. Chances are I'm probably going to guess one that works. Unfortunately, I didn't. And I guessed 1 next. One thing you should realize is teachers and authors like the number 1 as a 0. And a lot of times I will even check that first. So I did my synthetic division. This time I found my bottom row, I had some positive and some negative, so it's not an upper bound. And I know that 1 doesn't work. Now my only option left is 2. So that's what I guessed next. And I found it went in evenly. I know that because my remainder is 0. Now I could have found that none of these worked because Descartes counts the number of positive real roots. These are the possible rational roots. So there may be an irrational root out there that works and there are not any rational reals. That's rather discouraging when that happens. But in general, when this problem's written, you should be able to find a rational root that works somewhere. Now that I know that 2 is a 0, I can write my function in factored form. So if 2 is a 0, I know x minus 2 is a factor. F of x is x minus 2 times the quotient. X cubed, it's 1 degree less than what I started with, plus 8x squared plus 19x plus 12. Now, I always want to factor until prime, and I will try, if I can, to factor this part more using a traditional method because quite honestly, I hate the guess and check. But unfortunately for us, this does not factor by traditional methods. So I have to factor, I have to try again, and this time I'm going to factor just this part of my function. So I want you to, again, use Descartes' law of signs to determine the number of positive and negative roots. When you're ready for the answer, press play. So I did that, and I found that I have 0 positive real roots, which I expected because my function f had exactly 1, and I had already found it. The number of negative real roots, I did f of negative x, and I found that there were 3 sign changes, so it's 3 or 1. Next, I want you to list the possible rational zeros. Press pause on your video. When you're ready for the answer, press play again. So I wrote the factors of my constant, my numerator, divided by the factors of my denominator, or factors of the leading coefficient of my denominator, and then I listed my possible rational zeros from low to high. Notice, I only listed the negative ones because I knew that there were no positive real zeros. Now it's time to guess again. So I guessed -3 first, and I was very lucky this time because it went in evenly. When it goes in evenly, you just continue to factor. So I took my function, I knew that x minus 2 was still a factor. Now I know x plus 3 is a factor, times my quotient. X squared, it's 1 degree less than what I started with, plus 5x plus 4. Now, I did not come up with the lower bound first, but I want you to see what it looks like if I had. I used -12, and I found that the bottom row of my synthetic division alternates from positive to negative, positive, negative, positive, negative. 0 is a wild card, it can count as any, and -12 is a lower bound. Unfortunately, in this case, it's not very helpful because -12 is the lowest zero. But if others had been written that are lower than that, I'd be able to cross up anything that's lower than -12. Now, looking at our function at this point, it is still not prime. Although, by the time I get to a quadratic, I should either be able to factor it or I should be able to use quadratic formula to find the remaining zeros. So, it's still not prime. It's time to factor it again. So, when you are ready for the answer, press play again. I want you to factor the remaining quadratic. So, this factored as x minus 2 times x plus 3 times x plus 4 times x plus 1. The roots or zeros are 2, -3, -4, and -1. And that was a lot of work for one problem. Now, I want to summarize. When you are faced with a factoring problem for higher order polynomials, the first thing that you're going to try to do is you're going to try to factor first. You do not want to guess and check if you don't have to. The next thing you're going to do is you're going to find your possible rational roots using the rational roots theorem. You're going to narrow down the possibilities using Descartes and upper and lower bound tests. When you find a factor that works, you're going to rewrite it in factored form, and you are going to try to factor the quotient. If the quotient will not factor easily, you're again going to do the guess and check, use P's and Q's, and you're going to repeat this whole thing until it is prime. So I would like you to now get some practice, work on the assignment that is posted online.